Hi everyone, welcome to Vedantu English. I'm Diksha Kaushal, your chemistry master teacher. So everybody, welcome to the class and this is lecture 2 of DNF blocks where in lecture 1 we have discussed some properties of DNF block, like we have discussed about ionization enthalpy, atomic size, we have discussed the electronic configurations and how to remember these elements, right? So lecture 1 is also very important. In lecture 2, this is actually most important lecture from this particular chapter. Why am I telling you that? Because in this particular lecture, we are going to discuss about all the things: oxidation number, magnetic moment, and electrode potential, three most important properties of DNF block elements, right? So I know this is quite confusing, especially electrode potential questions can be confusing to you. So what I have done is all the concepts plus the NCERT important lines, right, with the explanation of that from where the question they can form, right? And trust me on that, if I am saying that no question will be out of this, no question is going to be out of this, right? Okay, so everybody, shall I start the lecture? If you're ready for the class, then let me know in the chat box. If you guys are ready for the class, then let me know in the chat box so that we can start with our class. And I gave you one homework for your this enthalpy of atomization. I gave you one homework, and I saw none of you actually did the homework. Huh? None of you, not even a single student has done the homework. Then how you are going to remember all this data, all the facts, right? So you also have to do hard work on your side. My task is to tell you that this is important. I can make you understand these things. I can teach you those things, right? But next thing, revision and homework that I can't do, that you have to do. You also have to put in some efforts here, right, students? Okay. So let's start with this. Firstly, it's okay if you have not done this. Today also I'll give you 2 questions for homework and I want you guys to do it, right? Promise me that you will do it, right? So, enthalpy of atomization, if you see, this is the data. We know that scandium, titanium, vanadium, karman, kujan. Okay, so till 21, from 21 till 30, we have written it here. So as you can see, maximum is for vanadium, right? Maximum and minimum for zinc. Firstly, this you should remember. This is maximum because this has higher chances that they will ask you this. Maximum and minimum has the maximum chances, right? Data, I feel, is less chances are there, but still you should remember it, okay? So vanadium, after vanadium, if you see 473, that is titanium. After titanium, you can see you have cobalt. Then you have, after cobalt, you have iron. Then I think after 416, you have chromium, right? Then chromium is done. Then after chromium, you have 339, that is copper. Then you have scandium, right? Now I think 3 is also done. Now you have, that's it, manganese and zinc. Let me see if these are 10. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Which we have not written. Scandium, titanium, vanadium, karman, pico, nickel we have not written. Where is nickel? Nickel is 430. So nickel is after before cobalt there should be nickel. Okay. So vanadium, titanium, then you have nickel, then you have cobalt. Vanadium, then you have titanium, then you have nickel, then you have iron. Then you have nickel, then you have cobalt, then you have iron. Okay. So this is actually your date from the data from your NCERT data only it is, right? Please don't see any data other than NCERT. You have to focus on NCERT data only, right? According to NCERT data, this is the order of enthalpy of atomization. Remember minimum and maximum, that is a must for you, right? Okay. Now guys, let's start with oxidation numbers. Okay. First is oxidation number, that is going to take time. Then we will see electrode potential, then third will be magnetic moment. Other properties are very, very simple. Okay. So if you talk about oxidation number, right? Oxidation number means how many electrons it has lost. For example, if I say zinc, right, you will see Zn2 positive, right? Scandium, you will see Sc3 positive. So the number that is written here is actually the oxidation number, right? So now what we have seen that in D block elements, they have variation of oxidation number for each element, right? Every element is possessing more than one type of oxidation number. That I'll show you in this particular table. This table is from your NCERT. As you can see in this table, right, you will see scandium is having 3, zinc is having only 2, titanium is having 3 oxidation numbers, vanadium is having 4 oxidation number, chromium is having 5 oxidation number, manganese is having 6 oxidation numbers, right? Iron is again having 4, then 3, then 3, then 2, then 1. Variable oxidation state is there, right? That means oxidation state is changing, right? Now, ma'am, what are these red circles that you have marked, right? So these red circles, you will see this your NCERT also, right? They have made these oxidation states in bold numbers, right? What do you mean by that? These red circle means that these are the most stable oxidation state for that particular element, right? So if you see scandium, you will see mostly in scandium 3 positive. It is the only oxidation state. For titanium, you will see titanium 4 positive is the maximum stable oxidation state. For vanadium, 5 positive is the maximum stable oxidation state. Then chromium, you have +3 and +6 oxidation state is stable. Manganese +2 and +7 oxidation states are stable. Iron +2 and +3 are stable. Cobalt +2 and +3 are stable. Nickel +2 are stable. Copper +2 is stable and zinc +2 is stable, right? Okay. So let's talk about, firstly, you should remember these oxidation state, that for each element, which of the following oxidation state is stable, right? That is the first thing. Now let's understand why it has variable oxidation states. So the reason behind, right, reason behind the variable oxidation state, this can be the assertion, okay? This can be the assertion that they have given you that D block elements have variable oxidation state. Reason they have given you this and that. So what will be the correct reason here, right? Correct reason is due to similar n-1 D and ns orbital. Because of the similar size of these two orbitals, they are going to travel from ns to n-1d. That's why they will have variable oxidation state according to that, right? So that is going to be the reason behind that. Now, let's understand how they are going to vary, right? So across the period, oxidation state increases. It is maximum at the center and then decreases even if atomic number increases. So what you can see, right? Across the period, oxidation state is increasing, right? That means if you see oxidation state is increasing, it is maximum at the center, right? In the center, can you see this is +3, this is +4, this is +5, this is +6, this is +7. It is increasing along the period. It is increasing. Maximum oxidation state is increasing along the period, right? Then it is maximum at the center. What do you mean by center? Center here means we are talking about manganese. All these are lines of your NCERT, right? So it is, these are direct NCERT lines, right, that I have picked up. So that's why I'm saying this lecture is very beneficial for you, right? And then decreases even if atomic number increases. So now, can you see it is decreasing? Can you see it is decreasing, right? It should be +6, +4, +4, then +2, but now it is +3, +3, right? So that's why along the period it is increasing, then it is maximum, then it is decreasing. That you should remember, right? Now, why it is so? The element which shows highest oxidation state is in the middle or near middle. Now, let me ask you, this question they can ask you, which of the following shows highest oxidation states, right? So, highest oxidation state in the 3D, in 3D series, it is shown by manganese. It is shown by manganese, and that is +7. And that is +7. And in 4D and 5D series, in 4D and 5D series, it is shown by ruthenium and osmium, and they are showing +8 oxidation state. This is a very important factual question that they can directly ask you. Right? In 3D series, it's manganese. In 4D and 5D series, it's ruthenium and osmium. Now, ma'am, where is this ruthenium? You said that it should be in the center. This is the D block, right? This is D block. Can you see that this is D block? In the center, this is manganese. Can you see? This is ruthenium, and this is osmium, right? So, what I told you here, either in the middle or near the middle of the series. Isn't it near the middle of the series? This is 3D series, this is 4D series, this is 5D series. They are showing, this is showing +7, this is showing +8, this is also showing +8, right? Very important direct factual question that they can ask you, right? Okay, so I am giving you numbers, you just have to catch these numbers, okay? Now, next is order of stability and oxidizing power of this. Now, this is another concept from oxidation state. This is written, this is again a line of your NCERT, right? A paragraph of your NCERT, this is, that I am telling you in the form of questions, right? It's basically because NCERT is little complex, so I have simplified it for you, right? So see, order of stability and oxidizing power, how you can write it? One thing you should, if you remember in P block, what we learned, in P block, we learned that down the group, I'll just write it here, right? In P block, students, what we learned in P block, that is the difference between P and D block. In P block, we learned that down the group, what will happen? Down the group, lower oxidation state, down the group, lower oxidation state, stability increases or decreases? Increases, right? Down the group, lower oxidation state stability was increasing in the P block, but in D block, it is entirely opposite. In D block, it is down the group, higher oxidation state, stability will increase. Higher oxidation state, stability increases, right? Right? That thing you should remember, that is the difference in P block and D block. This is in P block, this is in D block. When we'll study P block, I'll tell you this particular thing in detail, how they ask you question based on this concept. Now let's see in D block how they ask you the question, okay? So this is a question, stability of oxidizing power of Cr, chromium 6, molybdenum 6 and tungsten 6, okay? So if you see this here, right, chromium, where is chromium? This is chromium, this is molybdenum, this is tungsten, right? 3D, 4D, 5D series. So they belong to the same group, right? Now, if they are belonging to the same group, so can I say that it is, can I simply write it as that this is chromium, molybdenum, tungsten, right? Now, we are saying that the stability of +6 oxidation state will increase down the group. That means if this is +6, this is +6, this is +6, then tungsten will have more stability of +6, right? Tungsten will have more stability of +6 oxidation state, which can also be written it like this, that this is chromium, this is molybdenum, and this is tungsten. This is the stability order of these ions. Now, when I'm writing this stability order, another thing they're asking is oxidizing power, right? Now, tell me, what is oxidizing power? Oxidizing power means to get itself reduced, that I want to get reduced, right? something has good oxidizing power, they want to oxidize someone, right? We have learned this in electrochemistry. Do you remember we have done electrochemistry chapter before this, right? Oxidizing power means to oxidize someone. That means itself it wants to get reduced. Itself it wants to decrease the, itself it wants to decrease the oxidation number. Decrease the oxidation number. That means the ability to go to lower oxidation number. Now, if you see this here, here we have in chromium you have 6, 5, 4, 3, 2. These are the different oxidation numbers that they can exist in, right? Now, this is not stable, so it would want to get its oxidation number decreased, right? It would want to get reduced. So that's why its oxidizing power will be highest, right? That's why its oxidizing power is going to be high. Oxidizing power order is going to be maximum for chromium, because chromium wants to exist in +3 oxidation state. So it will gain the electron and get itself reduced and oxidize someone, and that's why it is a good oxidizing agent, right? Okay. Everybody clear? Now, let's do next thing, that is transition metals also show zero oxidation state in the metal carbonyl complex. Now, this is another question that they can ask you. Why the metals, right, they show zero oxidation state? So, for this, what you have to see, that these all are exact lines of from your NCERT, right? So, this we will see in detail in coordination chemistry, right? In coordination chemistry, we are going to see the detail of this. So there are some ligands which are pi acceptor. What are these ligands? That we will talk about in the coordination chemistry. These pi acceptor ligands, for example, carbon, for example, you have CO. Carbonyl is a ligand, that is your pi acceptor ligand, right? So now in these kind of pi acceptor ligand, metal exists in lower oxidation state. Lower oxidation state. That is the reason, if you see this here, in this particular complex, if you see this, in this particular complex, nickel CO4, right? This you will see in coordination number. I am not going to talk about how we calculated the oxidation number. That we will see in coordination chemistry. But just remember that here the oxidation state is going to be 0, right? Why it is 0? Because whenever you have any pi acceptor ligand, then these transition metals, they behave in such a way that they want to exist in their lower oxidation state, right? That's why this particular, usually they want to exist in higher as they go down the group, but two things. They go down the group, they want to exist in higher oxidation state, right? But if you have a pi acceptor ligand, they want to exist in the lowest oxidation state possible, right? Okay. Now, another concept is that whenever they are justifying the oxidation, variable oxidation states, they are justified. See, because these metals are electropositive, right? So they need some electron negative element, right, to pair up and to make a bond, right? So there are two elements that they combine with, where these transition elements, they show variable oxidation state. One is fluorine, one is oxygen. And based on this, one very important question is that this table is shown in your NCERT. This is also a table of your NCERT. These are the lines of your NCERT. Let's understand what do you mean by these lines. Okay, let's understand that. See, if you look into this table, can you see one thing? These are the oxidation numbers that they have shown. These are the metals that they have shown. Can you see here? Let's focus on manganese, okay? Let's focus on manganese. We know that manganese is showing +7 oxidation state as well, right? So we can see first thing is that with fluorine, it is definitely existing in more than one oxidation state. Here it is +2, here it is +3, here it is +4. Chromium also is existing in +2, +3, +4, +5, right? +6, all these oxidation state, right? So why fluorine has this ability to make different compounds? Reason? Ability of fluorine to stabilize the highest oxidation state, right? It can oxidize +4 oxidation state. If you see this here, +4 oxidation state was not stable here. +4 oxidation state in manganese was not stable. It was not under the category of a stable oxidation state. But fluorine is able to make a bond with manganese under +4 oxidation state. Just the same way with chromium, it is making +5, +6 oxidation state. But we know that with chromium, +3 is stable, but still it is able to make with higher oxidation state. How? Reason is, this is the assertion that they can ask you. This is the assertion that fluorine has the ability to stabilize higher oxidation state. What is the reason? This is the reason behind that. Reason is, for sure it is because of the electronegativity, but let's see what is the proper reason behind that. Due to either higher lattice energy, as the case of COF3, or higher bond enthalpy in terms of higher covalent compounds. Now, what happens here? Because they have very high electronegativity difference, right? Fluorine is highly electronegative. That is why their structure, their lattice structure will be arranged in that way that it will be very difficult to break this, because of more polarity difference, they will have strong attractions, right? And that is the reason their lattice structure will be very difficult to break. And in the case of this, higher bond enthalpy is needed to break its covalent compounds to this in terms of the higher covalent compounds. Yes. Similarly, this thing, right? Either it can be because of the higher lattice energy in case of, you say, the compounds in which they are making ionic compounds, right? In case of covalent compounds, because these bonds will be very difficult to break. All the reason is because of the electronegativity of the fluorine, right? Now, if you see this here, oxygen is showing altogether a very different image here. If you see oxygen, if you see this here, manganese, it was forming +4 oxidation state to the maximum. But can you see this here? Manganese here, it is having 2x minus 14 is equals to 0. Can you see this is +7 oxidation state? Here, manganese was not having +7 oxidation state. But oxygen, with oxygen, it is able to make a compound of +7 oxidation state. Now the question is why? Fluorine was more electronegative, right? So fluorine should be able to do it. Why oxygen is able to make a higher oxidation state with manganese? Reason is its multiple bond, okay? The ability of oxygen to stabilize these higher oxidation state exceeds that of fluorine. It is even more powerful than fluorine. Reason is their multiple bonds. It is its ability to form multiple bonds to metal explain its superiority. So with one double bond, it is able to give +2 charge, right? With one double bond, it is able to give +2 charge. That means one oxygen atom is able to give +2 charge to that particular metal, that is manganese. That is the reason with oxygen, it is forming higher oxidation state, which is even more than as compared to fluorine. Okay? Yes, everybody? Clear? Let me know in the chat box if that is clear or not, right? See, every single slide is here a bomb of question to you. Every single slide, right? Every single slide is a question here, right? Tell me in the chat box if till now you have any problem, whatever I have discussed, right? Till now, I'll just summarize what we have discussed till now, because I know there are too many information here. See, we have discussed about the oxidation state, which is highly stable. Then we discussed that down the group stability increases. Then we discussed that with pi acceptor, it wants to exist in lower oxidation state. Then we discussed how oxygen is giving rise to more higher oxidation state as compared to fluorine because of the multiple bonds. Okay. Now, let's understand this very, very interesting two things regarding fluorine and iodine. Okay, tell me one thing, fluorine and iodine, which is more powerful, guys? Which is more powerful? Let's see this. Which is more powerful, right? Let's understand that, right? So, this is copper, this is F2. Now, if you see this here, copper is existing in zero oxidation state. Can you see this is X minus 2 is equals to 0. So, here copper is existing in plus 2 oxidation state. Now, I'll ask you one thing. One thing I'll ask you. This question should be there in your head when you saw this, okay? When you saw this, this question should be there in your head. Ma'am, why plus 1 is not more stable? Why plus 2 is more stable in case of copper? Let's see why I am discussing that. Why I am discussing that, right? Let's see this. See, if you talk about copper, anybody, what is the electronic configuration of copper? Copper is, ma'am, argon, 4s1, 3d10, right? You take out one electron here, this will become 3d10, which is a very highly stable oxidation state. It is a noble gas kind of configuration, right? So if you talk about Cu2 positive, it is giving you 3d9. Now, according to you, which should be more stable? We can see this, copper positive should be more stable. I'm saying it should be more stable. But how come it is copper 2 positive is more stable? Why it is so? So, what is happening here? Why this is happening? Why this is getting converted to Cu2 positive instead of Cu positive? Because this is a very, very powerful oxidizing agent. It will be like, I want to increase your oxidation number. Copper said, I can increase up to copper positive. He said, I am the Don. Okay. You are nothing in front of me. I'll change your oxidation number to plus 2. He said, but please don't do that to me. I don't want to change to plus 2. I'll be in an unstable configuration. He said, I don't care. I am fluorine. I am highly electronegative. I am in the electronegativity series. I have maximum reduction potential. If you see in the electrochemical series, fluorine has highest reduction potential. Highest reduction potential. That means it is a very good oxidizing agent. It is an excellent oxidizing agent. Oxidizing agent. It is the most powerful oxidizing agent in the series. Right? I showed you in electrochemistry. In the top, there was fluorine and lithium was having negative electrode potential, reduction potential. That's why lithium was a very good reducing agent. This was a very good oxidizing agent. That's why he said that no copper positive, I'll convert you into copper 2 positive because of the very good oxidizing power of fluorine, right? Okay. Now, let's talk about I negative, right? Similarly, what is happening? I negative is converting Cu2 positive to Cu positive, right? Fe3 positive to Fe2 positive. How? Because it is a very good reducing agent, right? It's a very good reducing agent. So that's why it is able to decrease the oxidation number of Cu2 positive to Cu positive and Fe3 positive to Fe2 positive, right? Okay, so this is very important. The reason why CuF does not exist, right? Reason why CuI2 and FeI3 does not exist, right? Okay, this is the question that they can ask you directly. Which of the following does not exist? CuF does not exist because fluorine is a very good oxidizing agent. It wants to convert it into Cu2 positive, right? It's like my life, my rules, right? So now iodine is a very good oxidizing agent. This you have seen in redox reactions as well, iodimetry, right? So it's a very good, it's a very good reducing agent, right? So what it will do, it will convert CuI2, it will not let it exist. But what will exist? CuI will exist. Okay. And because what it was supposed to be, it should be CuI2. It should be FeI3. But have you ever seen FeI3? It does not exist, right? Because of the good reducing agent, right? Because it's a very good reducing agent. It will reduce Cu2 positive and Fe3 positive, right? Okay. Now, on the similar lane, we have one more question, that is disproportionation reaction, right? What is a disproportionation reaction? A disproportionation reaction is an element will have some oxidation state, just like here it has oxidation state +1. On the product side, its oxidation will increase and its oxidation will decrease also. That means here oxidation will occur, here reduction will occur, right? So its oxidation is going to increase as well. Its oxidation is its oxidation number is going to increase as well. It is going to decrease as well, and that's how it is going to show disproportionation reaction, right? Now the question is, ma'am, why it is showing disproportionation reaction? Very important question. Okay, this question now we will understand after doing electrode potential. Okay, let's put this question on a hold. Okay, let's put this question on a hold, right? Okay, after studying electrode potential, I'll tell you why this particular reaction is occurring. Cu positive is a D10 configuration. See here, I know that here you had F2. That's why it got converted to Cu2 positive. But here you don't have any F2. Now, why here it is getting converted to Cu2 positive? What is the reason behind that? That we will see from the electrode potential data, right? Okay. Okay, everybody. Firstly, tell me, are you able to understand why this is questionable? Why this is questionable? Yes, students, Jay, Manjeet, Mutha. Tell me if you're able to understand why this is Hema, Ibu, Supriya, right? Now, ma'am, doubt why +7 state is unstable. I am not saying +7 state is unstable. Where I said +7 state is stable, I am not saying +7 state is unstable. It is in the stable state. See, I was saying that how come in fluorine is not able to make this kind of compound MnF7, but that means with fluorine it is not making a oxidation state of +7, right? But with oxygen it is doing so because of the multiple bond of oxygen, right? Obviously +7 is a very stable state. That's why KMnO4 has +7 state. Okay, right? Okay, now let's see this. For that, before that, let's do this question and then let's understand electrode potential to understand the disproportionation, right? So here the statement is CrO3 is a stronger oxidizing agent than MO3. Okay, if you see this, CrO3 is existing in +6 oxidation state. This is existing in +6 oxidation state. This is your JEE Mains 2025 question. And this is based on this particular thing that I taught you, right? This is from your NCERT, right? This is the concept of NCERT. And the way they are asking the question is, this is the question that they have asked, right? So, can you see how the concept is there directly from NCERT and how they are asking you the question, okay? And it was considered as a hard question, right? So, Cr6 positive, right? And this is molybdenum 6 positive. Down the group, higher oxidation state increases. This is more stable. So, this is more stable. That's why it's like, I don't want to get reduced. Oxidizing agent means itself reduced. Itself reduced. Itself reduced means to decrease the oxidation number. Because it is stable in +6, so it does not want to get reduced. So it will not reduce. But this is not stable in +6, so it would want to get reduced. Okay. it would want to get reduced, right? So we can say this is a stronger oxidizing agent, right? So it's a good oxidizing agent, right? That is true. Next is, this is more stable. No, this is less stable. So this is false, right? So statement 1 is true, statement 2 is false. So answer will be A is the correct answer here, right? Okay. Now, let's see standard electrode potential. Okay, what is standard? Now, this is a very, very important concept, and I have seen students getting totally puzzled in this concept, right? So, let's understand this, right? Okay. Oh, now you must have seen electrode potential diagram, reduction potential, that reactivity series where we have seen fluorine is having positive standard reduction potential, lithium was having negative standard reduction potential, right? Now, how we are able to write those values, right? By doing some experiments. But now let's understand these values depend on what are the things that these values depend on, right? See, first thing is you will have a metal that is, let's say, in the solid state, right? Firstly, reduction potential means to reduce something. That means, see, if I talk about the standard reduction potential, right, we are actually taking out electrons from them, right? So for that, let's understand this thing like this, that you have a metal which is a solid. Firstly, you will convert it into gaseous state, because ionization can happen only in the gaseous atom, right? So that's why I converted it into gaseous state. Now, after this, if I take one electron from here, if I take one electron from here, that will be converted to one electron. This will be metal, gaseous, and this is positive. If I take one more electron from here, this will be M2 positive. This is gaseous. If I take one more electron, this will be, let's say that we are making M2 positive. Okay, let's say you are making M2 positive only. Now, after this, we do hydration. We do hydration. Because all of these are getting converted to aqueous ions, right? So, this will be M2 positive aqueous, right? So, let's see what are the different kind of energies you are using, you require or you are releasing, right? So, let's see that. If you see from sublimations to sublimation, I am saying from solid to gaseous, right? Solid to directly gas. What is that? Isn't it sublimation, right? Do you remember that is sublimation, camphor? But see, we know that camphor can easily get sublimable, right? It can easily sublime, right? How? Just you need to put it in the atmosphere, it will do its work, right? Because it's a sublimable substance. But these metals like copper, gold, are these sublimable, right? You put copper and suddenly it is getting converted to gas. No, this doesn't happen, right? So these metals are not sublimable. They don't get into sublimation itself, right? So you have to give them the energy. So that means this is going to be the endothermic process where energy will be required, right? So delta H of sublimation, that is going to be positive, right? Energy will be required here. Now, whenever you take out electron from metal, definitely ionization in enthalpy 1, it is going to be, yes, 1, and this is IE2, right? So again, this is going to be endothermic, right? So it is going to be positive. Here also it is going to be positive because energy is required to take out electron here, right? So you will give the energy. Now, when you move here, whenever you do hydration, right, you provide hydration. In that case, these molecules get very happy. Like when you drink water, your body gets very happy, right? So similarly, when you provide water to this particular gaseous ion, it gets very happy. And in this case, hydration enthalpy is always released. This is an exothermic process. Okay, understood? Now, can you see there are 4 factors that it is dependent upon? It is dependent upon delta H sublimation. It is dependent upon ionization energy of 1, ionization energy of 2, and it is dependent upon hydration, right? Okay, these are the 4 factors, right? So there is one positive energy and there is one negative energy. Positive energy that is required is of sublimation, ionization enthalpy. Then negative is of the hydration. Okay, this is the whole case, right? Now we will understand one by one what is happening here, right? Okay, so if you see this, there is no regular trend in M2 to M values, right? So if you say that you are converting M2 positive to M, they are saying that there is no regular values that you will have. This is because their ionization enthalpies and sublimation enthalpies do not show regular trend, right? Sometimes sublimation enthalpy is more, sometimes this is less. So that's why there is no regular trend here. If you see this here, there is no regular trend in the electrode potential. It's not like it is decreasing, then decreasing, decreasing. Sometimes it is decreasing, then again it is increasing. So there is no regular trend here, right? But what you will see, right? What you will see, there are some very, very important points to discuss from this particular table, and that we are going to discuss, right? So why I showed you this, that also I'll tell you, because when we will study the reasons, then we will need this particular table, right? Okay, so let's understand this one by one. First is that copper shows a unique behavior in the series, right? Can you see copper is showing a unique behavior? Negative, 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 negative. It is the only metal which is showing positive electrode potential, right? Okay, so positive electrode potential, unique behavior in the series, that is only metal having positive value of E naught, right? Now the question arises that why it is the only element which is having positive value, right? Let's understand this, right? You will have copper, which is solid, right? Then it will get converted to copper gaseous. Then it will get converted to copper positive gas. Then it will get converted to copper 2 positive gas. Then here it will get converted to copper 2 positive, and this is the aqueous, right? Now, here we know that energy is required. Energy is required. You can just say endo, endo, right? Energy is required. Here energy will be required. Here energy will be required. Here energy will be released, right? Now, if you see this, copper is nothing but 4s1 3d10, right? This will be 3d10 and this will be 3d9. Now, we know that this is a very, very stable, this is a highly stable electronic configuration because it is fully filled, right? Because of this, right? Hello, 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 right? So, yeah, do you think that if he is not seeing your chats, then he will see my chat, right? So, now let's see this here. If I am saying that this 4s1 3d10 it is losing one electron and becoming 3d10, then after that it is losing one more electron, then only it can become 3d9, right? But we know that this is a highly stable electronic configuration because of fully filled d orbitals, right? Now, to take out electron from this, to take out electron from D10 is very tough. It is so tough, that is the reason very high, very, very, you can say very high IE is needed. Very high energy is required here. Very high energy will be required to take out electron from this very stable 3D 3D10 electronic configuration. But please see this thing here. This is gaseous. This is gaseous. I'll tell you why I'm telling you specially this. I'll tell you why I'm telling you specially this. This is gaseous. This is gaseous. Right? In gaseous state, Cu positive is more stable. Because of the electronic configuration, right? Now, because of its electronic configuration, it is to lose one more electron, it's very difficult. So very high energy is needed here. This energy is so high, that it makes the conversion very, very difficult, right? Okay, so this energy is so high that it overcomes this particular high hydration enthalpy, and that is the reason copper has positive reduction potential, right? That is the reason copper has positive reduction potential. Is that clear, everybody? Tell me if that is clear or not, right? Why it has positive reduction potential? Because of this particular case, right? Okay. Okay, everybody. Now, thank you, Kanika. Thank you. Right? So I hope so this is clear to all of you, right? We are converting this. This particular thing is the problem, right? Here is where the problem is lying, right? This is not able to convert this to Cu2 positive, and then this automatically becomes difficult, right? Okay, because of this particular difficulty process here, it is having positive electrode potential. Firstly, tell me, is that clear to everybody or not? Is that clear to everybody or not? I'll tell you one more thing, right? See, now you will ask me, ma'am, I know that some of you might be having this question, ma'am. What do you mean by this positive reduction potential? Hai na? What do you mean by that? Okay. So I'll tell you one very simple thing here. This is actually a way to remember this. Okay. So if standard reduction potential is less, is more, let's say it is more, it becomes conversion of M to M2 positive becomes tough. I'm saying becomes difficult, right? So if I am saying that this is having positive reduction potential, wait a minute, where it is? Yes. If I am saying that this is having positive electrode potential, that means from Cu to Cu2 positive, Cu2 positive, the change is very, very, very difficult. Okay. So this is a simple trick that you should remember. See, why? Because positive standard reduction potential, right? If standard reduction potential is less, then it will be easy to convert M to M2 positive, right? Okay. This is the funda which will make every single thing very, very easy for you. Just remember this thing. You just need to remember this thing. If standard reduction potential is high, then M to M2 positive conversion will become difficult, right? So we need to have less standard reduction potential if you want to convert this thing, right? If you have, see, simple thing is if standard reduction potential is high, then from M2 positive to M, it will be easy. It will be easy, right? So opposite will be difficult, right? Because the questions are asked this way, so that's why I'm telling you this thing, right? The questions will not be to convert Cu2 positive to Cu. No, they will give you Cu to Cu2 positive, is it possible or not? This is what they are going to ask you, right? Cu to Cu2 positive in the gaseous state, it is very, 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 very difficult. Why? Because it is having a positive standard reduction potential. Positive standard reduction potential means it is very difficult to convert it into Cu2 positive. Okay, right? Now let's see, because of this what happens, because it's very difficult to convert it into Cu2 positive is very difficult to convert. So that's why if you have any H positive here and this is getting converted to H2. Achha, tell me one thing. If you have Cu, this is Cu2 positive, right? This is H positive, this is H2. We know that this is oxidation, this is reduction. If Cu to Cu2 positive is difficult, will it be able to liberate H2 with any acid? No. Because if this conversion is difficult, then this conversion is also going to be difficult. And that is the reason this Cu, this explains why why Cu does not liberate H2 gas from acids. It will not be able to do this because it is not able to convert itself into Cu2 positive, right? So it reacts only with oxidizing acids like nitric acid or sulfuric acid, which are reduced, right? Which are easily reduced. The reason for positive E0 value for copper is that sum of enthalpies of sublimation and ionization is not balanced by hydration enthalpy. This enthalpy is so large, it makes the overall endo positive value so high that it is not balanced by hydration enthalpy, right? This is sublimation plus ionization is so high, which is not balanced by hydration enthalpy. Okay, this is a very, very important question. Okay, right? Okay, guys. Okay, okay. No, these are not going to be deleted or stopped, guys. Don't worry. Don't worry. We are here, right? Don't worry about that. Now let's see this question here. The electrode potential of this of 3D element shows positive value for what? Electrode potential. This is the question of JEE Mains 2021. Electrode potential is positive for copper, right? So can we say C is the correct answer? Yes, ma'am. Now, let's see some weird things. This is again a graph from your NCRT. Everything that I'm picking up is from your NCRT, guys. That is a Bible that you should know. Inorganic chemistry, for inorganic chemistry, this NCRT is a Bible, okay? So, let's understand this thing here. Let's understand this thing. Here, what they have told you, this is expected, this is real. This is expected, this is real. This is expected, this is real. This is an NCRT graph. So this is titanium, man, P, Ko, Ni, Ku, Jan. Can you see for cobalt it is different and for nickel it is different? See, they are giving you the expected electrode potential values and the real electrode potential values, right? So what they have observed is that for cobalt it is different. This was the expected, and this is the real value. This is the real value. This is the expected value. Now, why for cobalt and nickel, the expectation versus real is different, right? Let's talk about that, right? So, here we are going to talk about also one thing. See, for manganese, it was also expected that it is going to go down. But the question is, if it is going to go up, why it is going down in manganese, in cobalt and nickel? For manganese, it was expected because of its half-filled stable configuration. But for cobalt and nickel, it is questionable why this is happening. So all these three questions we will answer here. The values of E0 of manganese, nickel and zinc are more negative than expected. Can you see? They are turning out to be, this should be here, this should be here, it should be here. But they are more negative than expected. They are going down here. Why it is so? Why they are below? Why they are more negative than they expected? This is due to, firstly, for manganese, this is for manganese, okay? For manganese, it is because of the stability of Mn2 positive, right? Now, I'll just write it here, three sections I'll divide it into. First is manganese. From manganese 2 positive to manganese, right? This is negative. See, chalo, I'll talk about that. Standard reduction potential of manganese is negative, right? Reason, negative means less, right? Less means it is making it easy to convert Mn to Mn to positive. So Mn to Mn to positive is easy, but Mn to positive to Mn is tough. I'm simplifying these things for you, okay? If I am saying that the reduction potential is negative, right? What I told you here. If the reduction potential is negative, guys, if I tell you here that the reduction potential is negative, what do you mean by that thing? Reduction potential negative. Okay, I'll just I'll chalo koi baat nahi. I'll write it this way. That means M2 positive to M is easy. Becomes easy. If your standard reduction potential or you can just say this in simple terms, SRP is directly proportional to M2 positive, right? No, it is directly proportional to M2 positive to M and inversely proportional to M to M2 positive. What do you mean by that? If someone's standard reduction potential is high, it is easy to convert M2 positive to M. This you should remember, okay? I have made it even more easier for you, right? Even more. This is the same concept we are going to apply in next 10 questions. Same concept will be applied. If you have a hold over this thing, you will not find anything else difficult, right? So standard reduction potential is high. What do you mean? Is low. Now this means it is low, right? This low means from 2 positive to 0. That means decrease in reduction potential is going to be tough. Or you know what? You can just remember it like this also. Instead of writing it like this, you can just remember it. Oxidation number increase, decrease, and this is oxidation number increase, right? If reduction potential is high, it's easy to decrease the oxidation number, right? Just remember this thing, right? So now if you see that this is low, that means it is this is low means it is very difficult to decrease the oxidation number, right? So oxidation number decrement will be very difficult. Why? Because Mn2 positive is already in a very stable oxidation state, right? And completely filled D subshell for Zn2 positive. Now, why for Zn2 positive this is happening? For Zn2 positive, again it is very low, and that is the reason to convert Zn to Zn2 positive is very easy. To increase the oxidation number is very easy. But to decrease the oxidation number, that means to undergo reduction, it's very difficult. It's very tough because the reduction potential is very low, right? Now, the question is especially for manganese, especially for nickel. This is very, very important. Most important is nickel. See, for manganese and zinc, it was still predictable. But exceptional behavior of nickel towards E0. Why nickel is showing this exceptional behavior? Because the hydration enthalpy is very high, right? From the regular trends due to its high negative enthalpy of hydration. This is a very, 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 very important conclusion here, right? What you will see through the table also, I'll show you here the table as well, right? This is the table. If you see, this is nickel, right? In the nickel, can you see this is having exceptionally high hydration enthalpy, right? Okay, that is the reason because of this very high hydration enthalpy. This is not so high, this is not so high, this is not so high, but this hydration enthalpy is so high that it makes nickel as the very negative electrode potential. That's why, that is the reason that to convert nickel, for nickel to positive, right, it is low. That's why nickel to positive, that means increasing, will be very tough, will be very easy, right? But nickel to positive to nickel, it's very tough. Okay, it's very tough. Okay, guys, I hope so. This thing is clear to all of you, right? Okay, tell me if that is clear or not. Okay, tell me if that is clear, guys, right? Sanjay, Shweta. I would see, if you want to see the recorded version of GUC, it's already there in the last year lectures, right? You can go and watch that. But if you see the detailed videos, I'm going to come up with that. Don't worry, right? Okay. So let's see standard electrode potential. Okay. For M3 positive to M2 positive. Now, how do you define it? Same thing. Standard reduction potential, if it is high, then oxidation number decrement will be easy. Wait a minute. Oxidation number decrement will be easy, and oxidation number increment will be tough. Okay, this will be tough, this will be easy. Okay, this will be easy. Simple thing, right? Now instead of 0 to +2, we are doing +3 to +2. Okay, so now here you will see three things here. One is titanium. So some of the very, very important conclusions here. That is titanium, vanadium and chromium has negative, and manganese, iron and cobalt has positive. And based on this, we will do some questions. Okay, so let's see, let's verify this data here. So now they are saying that if you talk about the standard electrode potential, right, that is M3 positive to M2 positive, there are 3-4 lines that I have picked out for you, right? So one by one we will see those lines. Okay, so first line is from your NCERT, that is not NCERT, but yes, from the data given in NCERT, that is low value for scandium reflects the stability of scandium 3 positive. See, if standard reduction potential is low, that means its increase in oxidation number will be tough, right? So that means you can say if scandium, it has low or what? Low value of this, na? Then we can say scandium to scandium 3 positive, it's easy. To increase the oxidation number, it's easy, right? But to decrease the oxidation number, it's tough, right? So can we say if standard reduction potential is high, standard reduction potential is low, that means it is very difficult to reduce it. Now, can you tell me why it is so difficult why the value is so low? Because why to convert scandium 3 positive to scandium, it is so difficult? Why this value is so low? Why scandium 3 positive to 2 positive, it is so low? Because this is having, scandium is nothing. See, scandium is what? This is 4s2 3d1. Okay, scandium 3 positive is 4s2 3d0, which is a stable configuration, right? That's why it is so difficult, right? It has a noble gas configuration. It has a configuration of argon, right? That is the reason. Scandium 3 positive has a noble gas configuration of argon. That's why it is so difficult, right? Okay, right? Okay, yes. Now, let's see. Now, let's see this thing here. The highest value for zinc. Where, sir, student, right? There is example or not that I'll tell you by someday. I'll show you the, maybe next class only I'll show you the Tattva PDF. Now I have not downloaded it on the studio. Then I'll ask you where are the examples and where are the questions, okay? How this Tattva book is made, right? I'll ask you then, right? So, It is filled with examples and questions, and still you are saying this. I don't know which channel has sent you to spam here, right? So the highest value of zinc is due to removal of electron. Now we are saying highest value of zinc of Zn 3 positive to 2. So if you are saying that for electrode potential of Zn 3 positive to Zn 2 positive is very high, this means that this particular reduction is very easy. Zn 3 positive to Zn 2 positive, it's very easy, right? Why? Because Zn 2 positive is nothing but it is 3d10, which is a stable configuration, right? This is 3d9, which is not a stable configuration. So it would love to get converted to a stable configuration. That's why this has a very high standard reduction potential. Okay, right? Now, guys, I'm just simplifying these tough lines for you. Okay. Now, comparatively high value of manganese shows that manganese 2 positive is particularly stable. So, manganese also applies the same rule. See, manganese, if you see, electrode potential of manganese 3 positive to manganese 2 positive, if I am saying it's very high comparative to zinc, then can we say that, not comparative to zinc, we want to say that if you see this here, right, this is manganese, zinc has highest, manganese is after zinc, right? So zinc is not written here, but zinc will be the highest, right? So after that you will have the manganese, right? So let's see why why manganese is highest. What do you mean by that? That means manganese 3 positive to 2 positive conversion is very easy. Can you tell me why? Because this is nothing but D5. This is D4. So to convert D4 to D5, it's quite easy, right? So that is the reason. Next is comparatively low value for iron shows extra stability. Now, if you see this particular table, this is from your NCERT only. For iron, it is 0.77, which is comparatively low, right? So why it is comparatively low? Everybody, why it is comparatively low? So again, E naught of iron 3 positive to 2 positive, right? Comparatively low, that means it is quite comparatively slightly low. Okay, so we can say Fe3 positive to 2 positive is actually not that easy. Not easy. It's tough. Why? Because this existing in 4s2 3d6, if you take out 3 electrons, 2 plus 1 here, right, that will exist in, wait a minute, Fe3 positive, na? Wait a minute. 4s2 3d6, right? 1, 2, 3, yes. It will be in D5 configuration, right? Because it is 26 atomic number. It will have 4s2 3d6, right? You take out 3 electron, it will become 3d5, right? It will become 3d5. So can we say that this actually is a stable configuration? That's why it is very difficult to convert it into Fe, but still it's possible. It's not like it's a negative potential. It's not negative, but low, That's why it's not impossible to convert it. Like for example, here it was very, very difficult. If you talk about this Zn3 positive, this is highly unstable, right? Here Fe2 positive is not highly unstable, but it's not also that stable. Okay, right? Right? Yes. Now, let's talk about the next thing, that is, see students, I would always advise you one thing, that when you have time, then don't go for one shots, okay? Because this much detail, even I won't be able to teach you in one shots, okay? So, one shots are for revision purpose, right? And when you are very like near to the exam, but still That's why right now I'm picking up those chapters that in one shot it will be very difficult to cover those chapters, right? Okay. So let's talk about this. That is, next is comparatively low value of chromium is related to stability of Cr3+. I think this how much we have done, hai na? So let's talk about this. Okay, this is this is difficultly it's a different question. Okay, now if you talk about chromium, right? Can you see chromium? Chromium is a negative value. That means it is very difficult to convert. It is very difficult to convert chromium 3 positive to chromium 2 positive. It's very tough. It's tough. Why? Because it has a low value of chromium, makes it tough. Reduction potential is low, so its conversion is also low. Let's see. What is chromium? Chromium is nothing but 4s1 3d5. So chromium 2 positive is nothing but 3d4. Chromium 3 positive is nothing but it is 3d3. Okay, this is 3d3. So this we are going to talk about in coordination chemistry. That what happens? It has the 5 degenerate orbitals of d orbitals that are splitted up into. This is because of crystal field splitting that we will talk about in coordination chemistry, right? So this gets splitted up into 2 parts, and that's why this T2G level is making it highly stable, right? So this is one of the very important questions, that chromium 3 positive is 3d3. Why it is so stable? Because why it is so stable? That its conversion is very difficult because of this T2G stability that we will discuss in coordination compounds in the CFT theory. Okay, now this is the same question, right? Why chromium 2 positive is reducing agent but manganese 3 positive is oxidizing? Guys, what is the reason behind that? Let's see this. Okay, chromium is what? What is chromium? Chromium is argon 4s1 3d5. Manganese is argon 4s2 3d5, right? If you see that when you take out the electrons here, this is chromium 3 positive, that becomes 1, 2, 3, this becomes 3d3, and this manganese 3 positive becomes 1, 2, 3, 1, 2, 3, 3d4. Okay, now what happens, right? This because of its T2G configuration, because of its T2G, this is T2G, this is EG. This because of this T2G stability, right? T2G stability, right? This is stable because of T2G, right? Acha, we are asking about chromium 2 positive. Wait a minute. Then things will change, right? This is chromium. Chromium 2 positive is what? Chromium 2 positive is nothing but it is 3d4. See, now the question is that this is also 3D, this is also 3d4, this is also 3d4. Then why is that it wants to get converted to Mn2 positive and it wants to get converted to chromium 3 positive? That means it wants to get oxidized, right? It wants to get oxidized, it wants to increase the oxidation number, and this wants to decrease the oxidation number, right? Why it is so? Why they want to do it? Because on doing so it will be converted into chromium 3 positive, which is 3d3 configuration, which is stable due to this T2G half-filled configuration, right? T2G half-filled configuration will make this stable, but nothing like this happens in manganese, right? So manganese will not exist in T2G, and that is the reason that manganese would want to would want to gain one electron, right? And here what it will do? It will get converted to 3d5. After gaining one electron, it would want to get converted to 3d5. This is half-filled stable configuration. This is half-filled configuration, and this is stable due to T2G, right? Both have their own stability, right? Now, because here oxidation number is increasing, that's why it is a good reducing agent. Because here oxidation number is decreasing, so that's why it is itself getting reduced. So it says oxidizing someone, so that's why it is a good oxidizing agent. Okay, right? Bhanu Sai, I think you are not following me here, right? I have already completed chemical kinetics. I have already completed electrochemistry. I have already completed solutions, right? These chapters we have already done in detail, right? Okay, understood? Yes, everyone. Now, tell me if that is clear to all of you or not, right? I really doubt that today we'll be able to do all the properties. I think we need one more lecture. Let's do as much as possible. You know? Let's do as much as possible, right? So, next is chemical reactivity and E naught, right? Chemical reactivity and E naught. The metals of first transition series, right, except copper, are relatively more reactive than the other series, right? So let's see why they are more reactive except for this, because they have high, or you can say they have negative reduction potential. That is the reason. Okay, so let's talk about this thing. As already explained, less negative E naught values for this along the series indicated decreasing tendency to form divalent cation. This all I have already discussed, right? If M2 positive to M2, it is less negative, right? So what will happen? This conversion will be very easy, right? So if I say it is less negative, that means it is very low. Low means this reduction is very difficult. Okay, so that's why this conversion will become difficult and indicate a decreasing tendency to form the divalent cations, right? Okay, so this data we have already discussed, right? Let's talk about, I think this one is important. So I forgot to tell you this thing, na? I forgot to tell you this important part here, right? That is this one, where we were talking about yes, we were talking about disproportionation. Yes, this is a very, very important thing that I told you that I'll tell you after we discuss reduction potentials. Okay, so many copper positive, many copper this ions. Now the question is that I told you that this is the disproportionation reaction. The question is that why it is happening, right? Why this is being converted to 0? Why this is being converted to +2? The question is that, ma'am, if I told you that copper positive is having D10 configuration, this is copper 2 positive, this is having D9. If you remember, I just told you this. This was in gaseous, this was in gaseous. And I told you that here very high energy will be required. Ionization energy will be very, very high, that will be required. Do you remember? I just told you that this ionization energy is going to be very high to take out the electron. Then how come this is happening, ma'am? If the ionization energy required is so high, then why this is happening? In fluorine, we understood. In fluorine, see, it's understandable here. Here it is understandable. If you talk about, wait a minute, where it was. If you talk about this case, it's understandable. This F2 is actually providing that amount of energy, right? But what about this one? What about this one? Here there is no F2. Why now it is getting converted to CO2 positive? Reason being, the stability of this aqueous. In aqueous, this is highly stable. That's why I specially mentioned there that underline that there I specially mentioned that it is gaseous, right? There I specially mentioned that we are talking about gaseous. Okay. Do you remember I specially mentioned here gaseous and gaseous? In gaseous, yes, Cu positive is more stable. You require very high ionization enthalpy. But when we talk about the case of aqueous, right? When we talk about the case of this is aqueous, this is copper positive compounds are unstable in aqueous solution, because in aqueous solution you have hydration enthalpy also, right? So stability of CO2 positive rather than this is due to much more negative hydration enthalpy, because hydration enthalpy is it is releasing delta H hydration. I told you that hydration enthalpy, whenever there will be hydration, it will be released, right? In that case, in this case, you had gaseous ions, then you convert it into aqueous solution, then it was released, which was not so enough, right? But if you talk about this thing here, it is already in the aqueous solution, right? Already there is so much hydration enthalpy which is able to, right, compensate with the energy required for this transition, right, of CO2 positive, then this, which is more than compensate for the second ionization enthalpy of Cu, right? So you can say that delta H of hydration here is greater than ionization enthalpy of 2. That's why this is possible. Okay, right, everybody? Very good, right? Okay, now, let's do this thing, right? Okay, let's do some question also after this. Here it is. E0 values for reduction couple, that is, this indicates, wait a minute. E0 for reduction couple, this indicates that Mn3 positive and this ions are strongest oxidizing agent. So let me just see Mn and Cu. Let me just see the data as well, no? Mn and Cu. Okay. It has positive, right? Okay, based on that, they are saying something. They are saying that this has positive values, and that is why Mn3 positive and Cu3 positive, right? They can easily get reduced to cobalt-2 positive ions, are the strongest oxidizing agents, right? That means they are saying that it's very easy to convert Mn3 positive to Mn2 positive. It's very easy to convert cobalt-3 positive to cobalt-2 positive as standard reduction potential are positive. So decrease in oxidation number is easy. The decrease in oxidation number will become very, very easy here, right? Okay, right? Understood? So decrease in the oxidation number becomes very easy. That means these two are unstable. Okay? So whereas now this means, okay, that this particular conversion is very easy. This is unstable, this is stable, right? Now, when you talk about the opposite of this, that is for titanium, vanadium and chromium. Okay, let me just show you that. Can you see this here? Titanium, vanadium and chromium, it is negative. Now, negative means very low reduction potential, right? Now, what do you mean by if you have very low reduction potential? Tell me. They have very low reduction potential, low standard reduction potential. That means decrease in oxidation number is difficult, right? When I am saying that decrease in oxidation number is difficult, then can I just write it as that titanium 2 positive, vanadium 2 positive, chromium 2 positive, right? Titanium 3 positive to this, vanadium 3 positive to this, chromium 3 positive to this. Is it difficult or easy? this particular transition will become difficult or easy? These transitions are difficult or easy. Oxidation number decrement, standard reduction potential is low here. That means these oxidation number will become difficult, right? So that means this is more stable. This is more stable. This is more stable, right? Because oxidation number decrement is becoming difficult here, right? Okay, right? So that was the reason behind it. So now the question of JEE 2024. See, I know that you will feel that, ma'am, what you are teaching us, right? But when you will see this, you will feel that, yes, why I am teaching that, okay? Now you will feel that why I am teaching that, right? Okay. Number of ions from the following that have the ability to liberate hydrogen from a dilute acid is what? Yes, everybody, that has ability to liberate hydrogen from a dilute acid is what? Let's see that. Dilute acid is what? Anybody? So, these have very low standard reduction potential of M3 positive to 2 positive, right? E0 M3 positive to M2 positive is very low. That means it is negative. So can I say that again same thing, titanium 3 positive to 2 positive, it's tough. Chromium 3 positive to 2 positive, it's tough. Vanadium 3 positive to 2 positive, right? It is equally tough. So if I say that all these things are tough, then number of ions from the following have the ability to liberate hydrogen from a dilute acid. Now you have to tell, will they have ability? See, this means if this is tough, if I am saying that this thing is tough, that means they don't want to get reduced. Don't want to get reduced. Hydrogen, in the case of hydrogen, wait a minute. Ions will have the ability to liberate hydrogen from a dilute acid. Standard reduction potential here is very low, right? If the standard reduction potential is very low, it's very difficult to decrease their oxidation number, right? Then they don't want to get reduced. If they don't want to get reduced, then if you talk about H positive to H2, how they will oxidize, right? Okay, right? Achha, we need to compare this with the hydrogen as well, na? Yes. We need to convert this, we need to compare this with the hydrogen as well. The proper values, we need to compare this with the hydrogen, right? So if you talk about hydrogen electrode potential is 0. And for this titanium or chromium or vanadium, it's negative. See, if it has less reduction potential, right, as compared to hydrogen, then it can get reduced because we are comparing it with hydrogen. If it has less reduction potential as compared to hydrogen, then it is possible that it is able to liberate the hydrogen because it has less reduction potential, so that we can say, yes, they have capacity to give off H2, right? Last question of today, students. After other things, magnetic behavior I'll do in the next class, right? Okay, magnetic behavior, other catalytic properties, right? All the things we'll do in the next class, okay? Right? That is going to be on Monday, right? That is going to be on Monday, right? Okay. Otherwise, if I'll start doing everything, it will take another 1.5 hours, right? So let's finish this off. So if you see this, among cobalt 3 positive, titanium 2 positive, vanadium 2 positive, chromium 2 positive ions, one, if used as a reagent, now they are saying, among all of these, one if used as a reagent cannot liberate H2 from dilute mineral acid solution. It's spin only magnetic moment in, see, second time it is repeated. Now, this is in JEE 2022. This was in JEE 2024. See, 2 times already it is repeated. Okay. So, way of asking the question is different, right? We know that titanium, vanadium, and chromium, right, they have negative values as compared to this. Cobalt is having positive value. So, cobalt will not be able to liberate H2, right? So, cobalt will not be able to not liberate H2 because it is having positive value, right? Now, because it is not able to liberate H2, so cobalt, they are asking you spin quantum number. That I'll tell you in the next class. Okay? I'll tell you how to calculate magnetic moment. That I'll tell you in the next class, because next particular thing is going to be for this. Those who know, they can answer me. But next thing is going to be on magnetic behavior only. So we are going to talk about that in the next class. Okay? Right, everybody? Yes. Or do you want me to cover magnetic moment now? Rest of the properties plus KMNO4 plus K2Cr27 plus lengthenoid contraction. If you want me to cover that in the next lecture, I'll do that. Tell me what you want. Tell me, guys, what you want. What do you want? If you want to convert magnetic properties now, we can do that even now. Okay? We can do that even now. Or do you want it in the next class? Right? Because magnetic property is a lengthy topic, right? It's not difficult at all. It's very easy, right? Very easy. Right? If you want to do it now, we can do it now. Right? Okay? Chalo, I'll do it now. Okay? Yes, continue. Let's do it now. Right? Let's finish off magnetic properties so that on Monday we complete this chapter. Okay? Because exams are near. So I want that on Monday I'll take a like class of 2 hours or 2.5 hours. I'll complete DNF block then. Right? I'll complete lengthenoid contraction, lengthenoids, electronic configurations, everything that we are left with. I'll complete everything in the next class. Okay? Chalo, let's do it now. Now, when a magnetic field is applied in the substance, mainly 2 types of properties happens. Okay? In fact, I'll talk about 3 types. One is diamagnetic, then there is paramagnetic, then there is the ferromagnetic, right? That are in your syllabus. Otherwise, you have ferri also, you have anti-ferro also, but in chemistry you don't have, right? So diamagnetic is repelled by magnetic field. Para is weakly attracted by magnetic field, right? But ferro is strongly attracted by magnetic field, right? This is the definition that you should know. And you should know that how to calculate which one is para, which one is di. For diamagnetic, no unpaired electron, right? But for paramagnetic, at least one unpaired electron. At least one unpaired electron should be there. Okay? At least one unpaired electron should be there, right? So let's talk about this. What is the formula? As one of the students, he told in the chat box only, right? Okay. So mu is equals to under root n plus 2 Bohr magneton. That is the magnetic moment, where n is defining the number of unpaired electrons, right? And I'll give you one trick here. If number of unpaired electrons are coming out to be, let's say this is number of unpaired electrons, this is mu, right? If number of unpaired electrons are coming out to be 1 or 2, let's say 1 or 2 or 3 or 4 or 5, more than 5 it's not possible. I'll tell you how, right? So because you have only 5, in D you only have 5, right? So 1, 2, 3, 4, 5, then it will be 6, 7, 8, 9, 10. So maximum 5 is possible, right? So that's why we are talking about this. Either you apply this formula under root n plus 2, or directly you say 1, 1.8, 2.8, 3.9, 4.9, 5.9. Okay, here you can say 1.7. Okay. So if they ask you in JEE, they usually ask you in integers. It is approximately 2, it is approximately 3, approximately 4, approximately 5, approximately 6. Okay? I have just added 0.7, 8, 9, whatever you add, right? So that is a simple trick. Okay? You don't need to put the formula. You just need to calculate the number of unpaired electrons, right? Now what you will see is most of the transition metal atoms, ions, will be paramagnetic. That means they will have unpaired electron, right? In the presence, due to the presence of unpaired electrons, higher the number of unpaired electrons, higher will be the magnetic moment. Now, this is a chart that you will see here, right? Can you see with 0 it is 0, 1 it is 1.7, 2 2.8, 3 3.8, 4 4.9, 5 5.9, 4 4.9, 3 3.8, 2 2.8, 1 1.7. That's why I told you, just remember it directly. You don't need to calculate it with the help of under root n plus 2. Directly you can see from the number of unpaired electrons. Okay, right? Now, how do you define that? That I'll show you from the number of, wait a minute, yes. These are the two questions now. From these two questions, I'll tell you how to actually write down the magnetic moment. Okay, let's see that. Spin only magnetic moment in titanium, vanadium, and scandium. Okay, three things are given to us. Okay, let's do this. Titanium, first thing what you need to do, if you know the electronic configuration, you can easily solve this. See, this is 21, this is 22, this is 23. So here it is nothing but 4s2 3d2, this is 4s2 3d3, this is 4s2 3d1. Electronic configuration. Titanium 3 positive is, you take out 3 electrons, 2 from here, 1 from here, it is 3d1. Vanadium 2 positive is, you take out 2 electrons from here, it will be 3d3. You take out how many electrons here? Scandium, you take out 3 electrons, 1, 2, 3. So scandium 3 positive is 3d0. Can you see number of unpaired electron is, here number of unpaired electron is 1, number of unpaired electron is 1, number of unpaired electron is 3, number of unpaired electron is 0, right? And that is the reason here mu is becoming 1.7, mu is becoming 3.8, and here it is becoming 0, right? And that becomes your answer here, right? Tell me, is that clear? Is that clear? Chromium can show +6 oxidation state. Its +3 oxidation state is highly stable. Okay, +3 oxidation state is highly stable, right? That is the reason we are not saying it is not showing +6. I'm saying which one is highly stable here, right? Let's talk about this one. Pair of transition metal ions having same number of unpaired electrons, right? Discuss that. Let's do that. JEE Mains 2025 guys. Such a simple question, yeah. Such a simple question. Such a simple one. Will you do it yourself? I'll give you this to homework, okay? This is your homework, okay? This is your homework. This is homework, right? It's a very simple question. This is your homework. Write it down in the comment section A, B, C, D, which is the correct answer, right? Because easily you can do this, right? Same thing what I did here, you have to do the same thing, right? And you have to see which one has the same number of unpaired electrons. They will have the same magnetic moment, right? Next is, which of the following electronic configuration would be associated with highest magnetic moment? See, it is 7. Make 1, 2, 3, 4, 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. Here also it should be 1, 2, 3, 4, 5. And here also should be 1, 2, 3, 4, 5. Okay. Now here you have 7. 1, 2, 3, 4, 5, 6, 7. Number of unpaired electron is 3. 1, 2, 3, 4, 5, 6, 7, 8. Number of unpaired electron is 2. 1, 2, 3. Number of unpaired electron is 3. 1, 2, 3, 4, 5, 6. Number of unpaired electron is 4. So this has the highest number of unpaired electrons. So its magnetic moment will be the highest. Okay? Right, everybody? Right? Rathi, clear? Yes, Chandru, clear? Okay? Understood? So answer is going to be D is the correct answer here. Right? So we have done major properties we have done. We are left with colored compound, alloy formation, interstitial compounds. Then there is complex formations. Simple properties we are left with. Catalytic catalyst, why they behave as catalyst. So it will take us hardly 15-20 minutes to cover rest of the properties. Then we will do in the next class, I am telling you. In the next class, we are also going to cover these properties here. Majorly, these properties are cramming based because catalyst, you have to remember the catalyst here, right? And majorly easy properties only now we are left with. Some tough properties we have already done. Now the next part that is important is lanthanoids, right? F block elements, what you have to study. See, in F block, the difficult part is what to study, right? Because there's too much cramming out there, right? So I'll tell you what to study in F block. Then we will discuss KMNO4, K2CR2O7 in detail, these two oxidizing agents. So I'm going to complete this chapter on Monday, right? In the next class, I'm going to complete this chapter. So I would advise you guys, right? In today's lecture, see, we have discussed a lot of things, right? A lot of things we have discussed. And you know what? There was one question that was left here. What was that? It was this one. Wait a minute. Yes. Right? This question, right? Here I told you that cobalt is not going to liberate. So they asked the magnetic moment of cobalt. So you can answer this as well. Cobalt is nothing but 4s2 3d7, right? So cobalt 3 positive will be nothing, but it will be 3d6. So it's unpaired electron 1, 2, 3. If you see, it's unpaired electron, guys, 1, 2, 3, 4, right? So its unpaired electron will be 1, 2, 3, 4, 5, 6. So it will having 4 unpaired electron. That means the magnetic moment is 4.9, which is equals to 5. Okay. So magnetic moment will be 5 Bohr magneton, right? Okay. Ma'am, having problem in color. Don't worry, we'll do that. Don't worry, right? You are having problem in color, we will do that, right? So let me just show you what are the questions that you need to do here, right? The question that I gave you for homework is this JEE 2025 question and this one. Wait a minute. This one is we have not done till now, right? This is the first question, that is the calculated spin only magnetic moment of chromium 3 positive. You have to tell the first question for you, everybody, right? Then the second question is pair of transition metal. This is JEE 2025 question that you will do yourself. Write down in the comment section which is the correct answer. Okay, right? Okay. Next class, we are going to complete this chapter and I'll see you all on Monday. And let's finish this chapter. After that, we are going to start with coordination compounds, right? Okay. Okay then, guys. Bye-bye. Take care. See you all in the next class. And I'm waiting for your homework in the comment section, which is over here. You can see. You can do the comment over here. And I hope so you have liked the session also, because continuously I have been teaching, right? That's why my energy is a little bit low, right? So before I was teaching on neat structure of atom and then I just came here, right? So that's why I'm saying that too much we are doing for you, efforts we are putting for you. For that, you also have to put in some efforts, do the homework, write down the homework in the comment section. If you have any feedback, you can write it down in the comment section, right? And guys, here we have our DNA batch, which I'll just show you here. DNA, I'm saying. Here we have our Sigma batch of JEE 2026, right? So Sigma batch is for Sigma people like you, right? 5 months are left, right? So what you need is, at this point, you need regular live classes, syllabus completion promise, and then revision sessions. You need doubt sessions, right? Mock test after every 15 days. That is happening there in the Sigma batch. Quizzes you want in the live sessions, right? There should be leaderboard so that you're able to understand what is the level that you are in right now and what all improvement is needed. Good quality questions that are there in the Tattva module. So all of this you will see in the Sigma JEE batch, that is just at 4,999. The variations are already here. You can see this here. If you want not only the Sigma batch, but you want these quick revision cards for your revision when you are in December, right? You want to revise everything and just give the mock test, and these cards is what you need. And JEE Tattva modules will be provided to you in the hard copy. See, modules will be provided here also, but in this case, it will be in the soft copy version, PDF version. Here it will be provided in the hard copy version. That is your book, right? That will be provided to you. Not one book, so many books, right? So around chemistry has, I think, around 8 books. So you can see same for maths and physics, maybe more. That will be provided to you, right? Okay. Yes. Okay then, guys. Bye-bye. Take care. See you all in the next class. Bye-bye. Good night. Bye-bye.